In previous videos, we've been constructing the complex number system. It was a story of innovation, of inventing new mathematical objects and tools to help us solve more problems. How far can we take this innovation? Can we keep inventing new number systems, and what kinds of unusual properties can we give them? I already hinted that there are many more possibilities, and we will briefly look at some of them in this video. This is just a teaser. For more details, I will refer to other stuff on the web. First, allow me to recap what we did earlier, because it serves as a good model. We started from the real numbers, and we added a new number called I with a single defining property. It squares to -1. Then we just started doing calculations, such as distributing one sum over another, and we used the definition of I to get rid of its higher powers. We quickly discovered that every number can then be written as a linear combination of 1 and I. We can use this basic strategy when creating other number systems or more general algebraic structures too. You start from an existing system, you add one or more new elements to it, you define the properties of those elements, and then you start calculating. Very often you distribute one sum over another to obtain some new terms, and then you use the defining properties to simplify those terms. It's quite simple, really. Can you just invent anything you want? Yes, but remember you have to use calculations and basic rules of arithmetic to show that it works. If it doesn't, you should go back to the drawing board and try something else. As a first concrete example, let's start from the rational numbers. Notice that you cannot solve the equation x squared minus 2 equals 0 because the square root of 2 is not a rational number. So we just invent it. We write it like this, and we claim that it squares to the number 2. That is the property by which we define it. Then we start distributing again, and all of the higher powers of square root of 2 disappear, thanks to its defining property. So we quickly discover that we can write every new number as a linear combination of 1 and square root of 2, very similar to what happens with the complex numbers. You could say that these new numbers have a rational part and a rooty part, similar to the real and imaginary parts of the complex numbers. This is an example of a field extension. The rational numbers are a field, which basically means that they have a well-behaved addition and multiplication. Remember that we invented the rationals precisely for that purpose, to make addition and multiplication behave exactly as we want, including their inverses. When you extend a field with a new number, you write that compactly like this. You put the field on the left, and then the new number between square brackets behind it. That's just a bit of notation. All it means is the rational numbers extended with the square root of 2. The resulting number system can be used to solve x squared minus 2 equals 0. But not yet x squared minus 3 equals 0. You can extend again by adding the square root of 3 to your number system, and you can keep adding new numbers until you're happy. You can, of course, extend things that are not fields. For example, instead of extending the reals or the rational numbers, we can extend the integers. The integers are not a field because division doesn't work. Adding the imaginary unit I to the integers, we get a new number system known as the Gaussian integers. Geometrically, they form a lattice of discrete dots, all evenly spaced in both dimensions. This time, only the points with integer coordinates exist. The rest of the plane between the points is not part of the new number system. You can just keep using the complex operations we discovered earlier. Since these formulas only contain integers now, whose sums and products are also integers, the resulting complex number will always have integers as its real and imaginary parts. we say that this number system is closed under addition and multiplication. So when you multiply two of these dots, you will always get another one of the dots, never something that lies in between. Obviously, this number system is not closed under division and square roots, just like the integers themselves. These Gaussian integers hold many interesting secrets. For example, in this number system, the number 5 can be factorized, so it's no longer a prime number. Aleph Zero has a nice video that goes into more detail. And one of my personal all-time favorites is a beautiful math video by 3Blue1Brown that uses Gaussian integers and their prime factorizations to calculate the value of pi, believe it or not. I highly recommend it, it's an absolute treat. Links to these videos are in the description below. You can come up with many kinds of weird extensions and try them yourself. For example, you could extend the real numbers with a brand new non-real number k that squares to 0. Wait, what? That doesn't sound very useful. We already have a number that squares to 0. Yes, that's true, but you would be surprised about how useful these seemingly trivial innovations can be. Look up dual numbers on Wikipedia if you don't believe me. Actually, you probably already know plenty of non-real numbers or other mathematical objects that square to 0. For example, this non-zero matrix, when multiplied with itself, gives you a 0 matrix as a result. Or think of how 2 times 2 equals 0 in arithmetic modulo 4. If you don't know modulo arithmetic, that's okay, we will pick it up later when talking about group theory. The point is that non-zero things that square to 0 are not as weird as you might expect. And of course, you can also invent new numbers that square to 1. These can often be interpreted geometrically as reflections, because when you reflect a shape and then reflect it back again, you end up right where you started. So the product of two reflections doesn't do anything, which basically means that you just multiplied everything by 1. And that's why the square of a reflection equals 1. To learn more about non-real numbers that square to 1, check out the split complex numbers on Wikipedia. In future videos we will talk about geometric algebra. That's where we will take this innovative strategy to the max, introducing many new kinds of numbers or number-like objects. We will even invent new operations, new kinds of multiplication with very interesting geometric properties, such as reflections, translations, and rotations in higher dimensions. Speaking of higher dimensions, can we come up with interesting number systems in 3D, 4D, or higher? Vector addition works in any dimension, so addition will never really be a problem. But, as we've seen, finding a good multiplication is extremely hard. In 3D, it's not even possible to find any multiplication with inverses. But then, surprisingly, in 4D, it works again. The quaternions are a 4-dimensional number system with inverses. The only downside is that their multiplication does not commute. In 8 dimensions, there is another number system with division called the octonions. This time, multiplication is not even associative. So, these number systems are not as nice as the complex numbers. As we move to higher and higher dimensions, we keep losing many of the nice properties of traditional multiplication. But that does not mean that these number systems are useless or uninteresting. Quite the contrary. The fact that they lack certain well-known properties makes them interesting. For example, the quaternions can be used to study rotations in 3 dimensions. If you're wondering how a 4D number system can describe 3D rotations, that's an excellent question. I may try to answer that in a future video. Besides the reals, the complex numbers, the quaternions, and the octonions, no other number systems exist that have all the nice properties we want. This should not be surprising, given how many constraints are imposed on addition and multiplication. But we can still come up with interesting algebraic systems that don't support things like division. We will look at geometric algebra later, where many higher dimensional systems of vectors and multivectors are studied. Those are incredibly exciting, and they contain many objects that behave more or less like numbers, even though you can't always divide by them. Okay, so in higher dimensions we keep losing many of the well-known properties of traditional multiplication. So you might ask, did we lose anything when we went from the one-dimensional reals to the two-dimensional complex numbers? The answer is yes. The real numbers can be strictly ordered. Given two different real numbers, you can always say that one of them is less than the other. This creates a relation between real numbers called a total ordering. And, more importantly, the ordering relation cooperates with the arithmetic operations, such as addition and multiplication. For example, if you multiply both sides of an inequality with the same positive number, the inequality still holds. When you multiply both sides with the same negative number, the inequality flips around. But in two dimensions this is no longer the case. You could in principle come up with a total ordering for the complex numbers, but it will refuse to cooperate with the arithmetic operations. Multiplication in particular is a problem because it rotates the plane, so that x and y coordinates can change their relative positions. This makes it impossible to come up with a well-behaved ordering relation. So, when going from 1 to 2 dimensions, we lose total ordering. This is not a big deal in practice because complex numbers are so incredibly useful and they still obey all the other rules of arithmetic. We didn't lose much. Are we done now? No, not even close. There seems to be an endless list of new number systems. Think about some of the equations that we still cannot solve. For example, the equation x equals x plus 1 has no solution. Well, at least not a real number solution. It would seem to suggest that 0 equals 1, which is clearly nonsense. Or is it? Or what about division by 0? This is not possible, but maybe we can come up with a new number whose value is 1 over 0. Maybe something like infinity. Can we inject infinity into a number system and make it work? How much is infinity plus 1? Or infinity to the power of infinity? Mathematicians are constantly pushing the boundaries. I won't go into any of the details here. If you're intrigued by these kinds of questions and you're not afraid to dive deep into some very weird math, you might want to look up things like the hyperreal numbers, surreal numbers, the book On Numbers and Games by John Conway, p-adic numbers, and many more. I will leave a few links in the description below. Or you could try your own experiments. You can create whatever you want, but then you have to prove that it works. You have to show that your new numbers don't break math, and that they are useful or at least interesting. To learn more, much more, remember to watch the videos in the description. I've also linked to some Wikipedia pages with more details, and to my Patreon page where you can support all angles if you find this channel valuable. In return for your support, you'll get early access to new videos, and you can hang out with the community. Please subscribe to the channel to make it more visible. It helps not only me, but the many other people who like learning about math. Thank you.